Bismillahirrahmanirrahim. Assalamu alaikum. So in the previous video we have seen that this space is a space of stochastic processes such that those stochastic processes FTW are adapted to the filtration FT, and also these stochastic processes satisfy this particular estimate. So this quantity is finite. So we have this space. Now we are interested in defining the Ito integral or the stochastic integral for the processes in this space. So for any given process from this space, or you can say that a function from this space, we want to define the quantity called stochastic integral or Ito integral, which is the integral of this function or the stochastic process from this space with respect to the Brownian, or it is also represented by W sometimes, R. So let's A to B, or A to B f of TW d bt. So this bt is in some books referred as WT. So this WT or BT, so this is representing my Brownian motion. I'm interested in defining this Ito integral or the stochastic integral. So let's get started. Like we defined the Wiener integral into some steps, so this particular integral will also be defined into 3 steps. So in the step 1 we will define this Ito integral or the stochastic integral. For step 1 we will pick a function from the space that we have defined. Let this function be step function. And instead of taking a general function, let's take a step function. So I hope you know what we mean by step function, or more precisely we mean a function of this type f of tw is equal to summation I equal to 1 to n of xi I minus 1 of omega times indicator function on the interval ti minus 1 to ti of t. So this is how we define the step function. So first we will define the stochastic integral for step function, like this kind of function, and it is defined as like this. Okay, so before I define, I need to put some more assumptions. So like this xi I minus 1 is fti minus 1 measurable, ti minus 1 measurable, so it's measurable in this filtration, and also the expected value of this xi I square is finite. I minus 1 value is finite. So now let's define the Ito integral for this particular kind of function. So for a given step function, the Ito integral from A to B of this step function is defined as, it's a sum from I equal to 1 to n xi I minus 1 times b of ti minus b of ti minus 1. So that's how we define the Ito integral for step function. And indeed you can see that if we represent this integral as an operator I acting on f, and f is a step function coming from the space that we defined in the start of the lecture, then we can see that as an operator this is linear. So for any two functions, step functions, it satisfies this linearity property, right? So that means for step functions we define the Ito integral in this way, and it is linear. Additionally, expectation of this I of f, or the expected value of this Ito integral of this step function, is 0. How this is 0 we can see later, and also the expected value of the square of this Ito integral of a step function is given by a to b expected value of f of t squared dt, this way. So the Ito integral of a step function satisfies these three conditions. The proofs for these two can be done, but I'm skipping for the moment. If you need to know the proof of this, you can comment down and we can contact and we can have a session and we can discuss that, because that will go on the lines of Wiener integral as we did previously. So Ito integral for the step function is defined in this way, and its expectation is 0, and its expectation of its square is 0. In other words, you can say that variance of this Ito integral is given by this a to b expected value of f of t square dt. So you can say this is variance, right?